There is a shade of red on the walls of Pompeii that no laboratory on Earth can produce. Not because the chemistry is unknown, not because the materials have vanished, but because something in the process, some step, some timing, some craft passed from hand to hand for centuries, disappeared when the last Roman pigment maker died without writing it down. That red has been sitting in the open air for nearly 2,000 years, exposed to volcanic ash, rain, sunlight, and the hands of millions of tourists. It has not faded. Modern red pigments, manufactured under controlled conditions with precise chemical formulas, begin to degrade within decades. The ancient red endures, and nobody alive can explain exactly why. This is not an isolated case. Across the ancient world, from Egyptian tombs to Chinese burial shrines, from Maya temple walls to medieval European cathedrals, civilizations produced colors so vivid, so stable, so impossibly durable that modern materials science, a discipline equipped with electron microscopes, mass spectrometers, and computational chemistry, still cannot fully replicate them. These were not accidental discoveries, they were technologies, carefully developed, carefully guarded, and carefully lost. Consider Egyptian blue. It is the oldest known synthetic pigment in human history, first manufactured roughly 4,700 years ago. Its chemical structure, calcium copper silicate, was identified over a century ago. Scientists know exactly what it is made of. They know the temperature range required for its formation. They have reproduced the crystal structure in laboratories dozens of times. And yet, every modern recreation falls short of the originals. The ancient pigment fluoresces under near-infrared light in ways that modern versions do not. The particle distribution is more uniform. The color is deeper, richer, more luminous. Something about the ancient manufacturing process produced a material that modern chemistry can describe but not equal. Now multiply that single failure across every continent, every era, every civilization that mastered color. Tyrian Purple, a barium copper silicate, was produced in China more than 2,500 years ago by a process so precise that it required control of temperatures exceeding 1,000 degrees, a feat that supposedly could not have been achieved with the technology available at the time. Maya blue, a pigment found on the walls of Chichen Itza, is so chemically stable that it has survived over a millennium of tropical heat, humidity, and torrential rain without fading. When researchers finally identified its composition, a combination of indigo dye and a clay mineral called palygorskite, they assumed reproduction would be straightforward. It was not. The binding mechanism between the organic dye and the inorganic clay operates at a nanoscale level that modern chemists have only recently begun to understand. Tyrian Purple, the legendary dye of emperors and kings, required the harvesting and processing of up to 12,000 individual Murex sea snails to produce a single gram of usable pigment. The exact fermentation and reduction process used by Phoenician dye makers remains a subject of active scholarly dispute. These are not curiosities. They are evidence of something uncomfortable, that ancient peoples, working without any of the tools we consider essential to chemistry, achieved results we cannot match. The knowledge required to make these colors was not theoretical. It was embodied, held in the hands, the timing, the instincts of craftspeople who learned by watching, by doing, by failing, and by passing their methods to the next generation in workshops and guilds that no longer exist. And this is what makes the story of lost pigments different from other stories of lost technology. When a library burns, we know what we have lost: titles, authors, ideas. When a pigment recipe vanishes, we are left staring at the result on a wall, unable to reverse engineer the journey. The destination is visible, the path is gone. By the end of tonight, you are going to understand not just which ancient colors have been lost, but why their loss matters far more than you might expect. These pigments are not merely beautiful relics. They are windows into entire systems of knowledge, chemical, geological, biological, and cultural, that took centuries to develop and vanished in the span of a single generation. The loss of a pigment recipe is not the loss of a color. It is the loss of a way of understanding the material world. Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. The first colours were not made, they were found. Somewhere in the deep past, a human hand reached into the earth and pulled out a lump of red ochre, iron oxide, the simplest pigment imaginable, and smeared it on the wall of a cave. That moment is among the earliest evidence of symbolic thought. Ochre fragments found at Blombos Cave in South Africa suggest that humans were deliberately processing pigments at least 100,000 years ago, according to current archaeological estimates. They were grinding, mixing, and storing colour long before they were farming, long before they were writing, long before anything we would recognise as civilization existed. But ochre is easy. It is a mineral. You dig it up, you grind it, you mix it with fat or water or egg, and you paint. The real revolution in colour, the moment that separates decoration from chemistry, came when someone, somewhere, decided that the colours available in nature were not enough. That moment, the decision to create a colour that does not exist in the ground, marks the birth of synthetic chemistry. And it happened thousands of years before anyone used that phrase. The earliest known synthetic pigment is Egyptian blue, and its creation is one of the most underappreciated achievements in the history of human technology. To make Egyptian blue, you need 3 raw materials: a copper compound, silica in the form of sand, and calcium in the form of limestone or crucite. You grind them together, you place the mixture in a kiln, and you heat it to a temperature between 850 and 1000 degrees for a sustained period, likely many hours. If the temperature is too low, the reaction does not complete. If it is too high, the material melts into glass. If the ratio of ingredients is wrong, you get not blue but green, or grey, or nothing usable at all. The margin for error is extraordinarily narrow. And here is what makes this so staggering. The Egyptians had no thermometers. They had no way to measure the precise temperature inside a kiln. They had no understanding of stoichiometry, the branch of chemistry that governs the exact proportions of reactants in a chemical process. They achieved what they achieved through generations of trial and error, through careful observation passed from master to apprentice, through a tradition of craft knowledge that was never fully recorded in any surviving text. The recipe, if there was one, was held in human memory and human hands. The scholar Vitruvius, writing in the 1st century before the Common Era, provided one of the very few ancient descriptions of the manufacturing process for Egyptian blue. In his text De Architectura, he described the grinding and firing of sand, copper filings, and natron, a naturally occurring mineral salt. His description, however, is frustratingly vague by modern standards. He mentions no specific temperatures, no exact ratios, no firing times. For Vitruvius, these details were presumably obvious, the kind of thing a competent craftsman would simply know. For us, they are the gap between knowledge and ignorance. This gap, between what ancient sources tell us and what we actually need to know, defines the entire history of pigment loss. Ancient writers did not write technical manuals. They wrote descriptions, observations, passing references. The Roman naturalist Pliny the Elder, whose encyclopedic natural history remains one of our primary sources for ancient pigment knowledge, devoted substantial sections to the description of colours, their sources, and their relative value. He named pigments, described their appearance, noted where they were found, and even commented on their cost. But he was a compiler, not a chemist. He recorded what he saw and what he was told, the underlying processes, the temperatures, the precise mineral sources, the critical timing, were beneath the notice of a Roman aristocrat writing a natural history for other aristocrats. That knowledge belonged to the craftsman, and the craftsman did not write books. This is the fundamental tragedy at the heart of every lost pigment. The people who knew how to make them were rarely the people who wrote things down. In the ancient world, there existed a profound divide between intellectual knowledge and practical knowledge, between what the philosopher discussed and what the artisan performed. Pliny could describe the brilliant red pigment known as cinnabar, noting that it came from mines in Spain and was extraordinarily expensive. But the miners who extracted the ore, the craftsmen who processed it, the painters who understood which grinding method produced the most luminous particles, those people left no written records. Their knowledge was oral, embodied, and generational. When the trade guilds collapsed, when the workshops closed, when the last master died, the knowledge died with them. To understand the scale of this loss, consider the sheer number of pigments referenced in ancient sources that modern scholars cannot confidently identify. Pliny alone mentions over 30 distinct pigment names in his natural history, and for a significant number of these, scholars have no certain identification. What exactly was the pigment the Romans called purpurissum? It was clearly related to Tyrian purple, but the exact manufacturing process, and therefore the exact substance, remains disputed. What about the pigment called xerussa usta, described as lead white that had been transformed by fire? Modern chemists can heat lead white and produce various lead oxides, but the specific conditions described by Pliny suggest a product that does not neatly correspond to any single modern compound. These are not obscure references from fragmentary texts. They come from one of the most complete and well-preserved ancient encyclopedias in existence. If our best source leaves this many gaps, the true extent of what has been lost is staggering. The problem compounds when we move beyond the Mediterranean world. In China, the development of synthetic pigments followed an entirely separate trajectory, driven by different raw materials, different kiln technologies, and different cultural imperatives. Han blue and Han purple, two barium copper silicate pigments that have no natural equivalent anywhere on Earth, were manufactured during the Warring States period and the Han dynasty. Their creation required not only high temperatures, but also access to barium minerals, which are uncommon and difficult to process. The specific combination of barium, copper, and silica at the precise temperatures required to form these crystal structures represents a level of chemical sophistication that Western chemistry did not achieve until the 19th century. And yet, the Chinese craftsmen who developed these pigments left no surviving technical records of the process. The pigments appear in tombs, on terracotta warriors, on ritual objects, but the workshops that produced them have never been found. The oral tradition that sustained their production died out sometime during the first few centuries of the Common Era. When exactly, and why, remains unknown. In Mesoamerica, the Maya achieved something perhaps even more extraordinary. Maya blue, the brilliant turquoise pigment that adorns the walls of temples and the surfaces of sacrificial vessels, is a hybrid material, part organic, part inorganic, that represents a category of chemistry so advanced that it was not even conceptually understood by Western science until the 20th century. The pigment consists of indigo, an organic dye extracted from plants of the genus Indigofera, bonded at the molecular level to palygorskite, a clay mineral with a needle-like crystal structure containing nanoscale channels. The indigo molecules enter these channels and become locked in place, protected from the chemical reactions that normally cause organic dyes to fade. The result is a pigment of extraordinary stability, resistant to acids, alkalis, solvents, and biological degradation. The first Western scientists who analyzed Maya blue assumed it was a simple mineral pigment. When they discovered it contained an organic component, they were baffled. Organic dyes are, by nature, fugitive. They fade. That is their defining weakness. The Maya had found a way to make an organic dye permanent by imprisoning it inside an inorganic crystal lattice. This is, in modern terminology, a nanocomposite material. The Maya were producing nanotechnology, and they were doing it centuries before Europe even had a word for chemistry. But who developed this process? How many generations of experimentation did it require? What failed recipes preceded the successful one? We do not know. The Maya writing system, while partially deciphered, contains no known technical treatises on pigment manufacture. The knowledge was held by specialists, painters, priests, craftspeople, and transmitted through apprenticeship and ritual. When the civilization that supported those specialists collapsed, the knowledge collapsed with it. This pattern repeats across every civilization that produced advanced pigments. The knowledge was precious, the knowledge was powerful, and the knowledge was fragile, because it lived in people, not in texts. And people, unlike texts, cannot be copied. The Roman world provides perhaps the clearest illustration of this fragility. At its height, the Roman pigment trade was enormous. a vast commercial network that stretched from the cinnabar mines of Almaden in Spain to the indigo sources of India, from the ochre deposits of the Aegean to the Murex harvesting grounds of Phoenicia. Pigments were among the most expensive commodities in the Roman economy. Pliny records that certain shades of Tyrian purple sold for more per weight than gold. The industry that supported these pigments, the miners, the dye makers, the paint grinders, the chemical processors, employed tens of thousands of people across the Mediterranean. It was a sophisticated, specialized, deeply knowledge-intensive industry. And then Rome fell. Not all at once, but slowly, over centuries, the economic networks that sustained the pigment trade contracted. Mines were abandoned, trade routes became impassable. The urban workshops that had supported generations of specialized craftsmen emptied as cities shrank and populations fled to the countryside. The market for expensive pigments collapsed along with the wealth and stability that had sustained it. One by one, the most complex and demanding pigments fell out of production. Egyptian blue, which had been manufactured continuously for over 3,000 years, ceased to be made sometime in the 4th or 5th century of the Common Era. The technique was not prohibited or suppressed, it was simply forgotten. The last craftsman who knew the recipe died, and no one replaced them. The medieval monk, Theophilus Presbyter, writing in the 12th century, attempted to compile a practical manual of artistic techniques in his treatise De Diversis Artibus. His work is one of the most valuable surviving sources for medieval pigment knowledge, and it reveals just how much had been lost since antiquity. Theophilus describes methods for making pigments that are, in many cases, crude approximations of Roman-era techniques. He mentions colours that he clearly does not know how to produce, referring to them as foreign or ancient. His description of blue pigments makes no reference to Egyptian blue, a pigment that had been in continuous use for 3 millennia before vanishing entirely. By the 12th century, the very existence of synthetic calcium copper silicate as a pigment had been forgotten. It would not be rediscovered until the 19th century, when archaeologists began analysing the blue paint on Egyptian artifacts and realised it was not a mineral. The numbers are striking. Of the major pigments known to have been in use during the Roman period, scholars estimate that roughly half had been lost or significantly degraded in quality by the medieval period. Some were later rediscovered or replaced by alternatives. Others were lost permanently. The net effect was a dramatic narrowing of the colour palette available to European painters, a narrowing that persisted for nearly 1,000 years. But the story of pigment loss is not merely European. In every part of the world where advanced civilizations rose and fell, the same pattern played out. Knowledge was developed over centuries of careful experimentation. It was held by specialists who transmitted it orally and through practice. When the social structures that supported those specialists collapsed through war, economic decline, epidemic, or cultural disruption, the knowledge vanished with them. What remained was the evidence: colour on a wall, pigment in a tomb, beauty without explanation. And this is where the real mystery begins, because the colours that survive are not just beautiful. They are, in many cases, chemically superior to anything we can produce today. They are more stable, more luminous, more durable. They represent a kind of mastery that we, with all our technology, have not yet recovered. Something is wrong with our assumptions. We assume that knowledge accumulates, that each generation knows more than the last. The history of pigments suggests a different truth. Knowledge is not a ratchet, it is a flame, and flames go out. Consider what this means in practical terms. Every ancient civilization developed its own colour vocabulary, not just words for colours, but the physical substances that embodied them. In India, the tradition of pigment making stretches back thousands of years, and the subcontinent produced some of the ancient world's most coveted colorants. Indian lac, a resin secreted by the scale insect Caryolaca, was harvested and refined into brilliant reds and violets that were traded across the Indian Ocean and into the Mediterranean. The processing of lac required intimate knowledge of the insect's life cycle, the timing of the harvest, and the precise methods of heating, filtering, and drying that transformed a raw biological secretion into a stable, workable colorant. In the workshops of Rajasthan, entire communities specialized in lac processing for generations. each family holding particular knowledge about local insect populations, seasonal variations, and refinement techniques. When British colonial policies disrupted traditional trade networks and imposed industrialized production methods in the 18th and 19th centuries, many of these family-held traditions fractured. The insects did not change, the skills did. In Japan, the art of producing traditional pigments, iwa enogu, mineral pigments ground to precise particle sizes from natural stones, remains one of the few surviving examples of an unbroken ancient pigment tradition, and its practitioners speak openly about how close their art is to extinction. The master pigment maker, Yukio Kuroe, whose family operated one of the last traditional pigment workshops in Kyoto, spent decades grinding minerals by hand into powders of graduated fineness, each grade producing a subtly different shade. A single mineral, azurite for example, could yield more than a dozen distinct blues depending on the coarseness of the grind. Coarse particles produced deep, dark blues. Fine particles produced pale, almost white-tinged blues. The skill lay not in knowing this fact, which any student could learn in an afternoon, but in feeling the precise moment when the grinding had reached the desired stage, a judgment of texture, sound, and resistance that required years of daily practice to develop. When Kuroe described his craft in interviews, he returned again and again to a single theme: the impossibility of teaching through words alone. "I can show you," he said, "but showing is not telling. You must do it yourself, 10,000 times, before your hands understand." This is the voice of embodied knowledge. Knowledge that resides in the body, not in the mind, and that cannot be transferred through any medium other than sustained practice under expert guidance. It is precisely this kind of knowledge that is most vulnerable to loss, because it cannot be stored, backed up, or archived. It exists only in the living practitioner. When the practitioner dies, it dies. The medieval Islamic world, during the golden age of scholarship between roughly the 8th and 13th centuries, made perhaps the most systematic attempt to bridge the gap between craft knowledge and written knowledge. Scholars in Baghdad, Cairo, and Cordoba compiled treatises on everything from metallurgy to medicine to the preparation of inks and pigments. The alchemical tradition, which in its serious scientific form was deeply concerned with the transformation of materials, produced detailed texts describing the manufacture of various pigments and dyes. The treatise attributed to Jabiya ibn Hayyan, the 8th century scholar sometimes called the father of chemistry, contains descriptions of processes for producing pigments from metallic compounds that show a sophisticated understanding of chemical reactions. But even these texts, among the most technically detailed to survive from the medieval period, fall short of what a modern chemist would need to reproduce their results. The language is often allegorical, quantities are approximate, temperatures are described in qualitative terms. A gentle heat, the fire of a lamp, a strong blaze, that could correspond to a range of hundreds of degrees. The Islamic scholars were writing for an audience of fellow practitioners who would fill in the gaps from their own experience. They were not writing for a future civilization that had lost the tradition entirely. The irony is acute. The Islamic Golden Age was, in many ways, the greatest period of knowledge preservation in human history, a civilization-wide effort to collect, translate, and systematize the learning of the Greeks, the Persians, the Indians, and the Chinese. And yet even this extraordinary campaign of intellectual rescue could not save the full depth of craft knowledge, because craft knowledge resists the very tools of preservation that work so well for philosophical and scientific texts. You can translate Aristotle, you can copy Euclid, but you cannot translate the feel of a kiln at the right temperature, and you cannot copy the instinct that tells a dye maker to stop stirring. And here, in this gap between what can be written and what must be felt, lies the origin of almost every lost pigment in human history. The philosophical texts survived because they were valued by literate elites who funded their copying and preservation. The craft knowledge perished because it was held by artisans who were rarely literate, rarely wealthy, and rarely considered important enough to record. The monk in his scriptorium copied Plato. Nobody copied the dye maker. There is a document, fragmented and incomplete, known as the Stockholm Papyrus, dating from roughly the 3rd or 4th century of the Common Era, It is one of the oldest surviving collections of craft recipes in the Western tradition. A manual describing the preparation of dyes, pigments, and imitation gemstones. Its recipes are terse, practical, and infuriatingly incomplete by modern standards. One recipe for a purple dye reads, in its entirety, grind separately and mix well. Dip the material. It takes the color. No measurements, no temperatures, no timing. The author assumed that anyone reading the recipe would already possess the background knowledge to execute it. The Stockholm Papyrus is not a manual for beginners. It is a collection of reminders for experts, a set of notes that presuppose the very knowledge we are trying to recover. It is, in effect, a key designed for a lock that no longer exists. The parallel Chinese document, known as the Qimin Yaoshu, a 6th century agricultural encyclopedia compiled by Jiaxixi, contains scattered references to dyeing and pigment preparation, alongside its primary content on farming and food processing. Its descriptions of indigo processing, in particular, provide tantalizing hints about the fermentation techniques used to extract the dye from plant material. But again, the level of detail is insufficient for confident reproduction. The text describes adding lime to the indigo vat until the color is right, a phrase that contains the entire problem of lost pigment knowledge in 6 words. What color is right? How much lime is enough? How do you know when you have reached the correct point? The author knew, his readers knew, we do not. The scope of this loss becomes clearer when we attempt to quantify it. Of the pigments and dyes known to have been in regular use across the major civilizations of the ancient world, Egypt, Mesopotamia, China, India, Mesoamerica, Greece, and Rome, scholars estimate that detailed, reproducible manufacturing knowledge survives for fewer than a third. For the majority, we possess either partial descriptions, ambiguous references, or nothing at all beyond the physical evidence of the pigment on surviving artifacts. We can see the color, we can analyze the chemistry, we cannot close the circle and make it again. The weight of this loss is easier to grasp through a single, concrete example. In the ruins of the ancient Roman city of Pompeii, preserved under volcanic ash since 79 of the Common Era, the walls of villas and public buildings display a palette of extraordinary richness. The most famous of these colours is Pompeian red, a deep, warm crimson that has become synonymous with Roman luxury. For over a century, the identity of this pigment was a subject of scholarly debate. Was it cinnabar, the natural mercury sulfide that Pliny described as one of the most expensive pigments in the Roman world? Was it red ochre, a far cheaper iron-based pigment that could be heated to produce a similar hue? Or was it something else entirely? A pigment or preparation method that did not correspond to any known substance? In the 1980s and 90s, a series of analytical studies using X-ray diffraction, electron microscopy, and Raman spectroscopy began to provide answers. And the answers were surprising. Many of the red walls at Pompeii turned out to be painted not with cinnabar or ochre, but with a mixture of the two, applied in multiple layers with specific techniques that exploited the optical properties of each pigment. The bottom layer was typically a coarse red ochre, which provided body and coverage. Over this was applied a thinner layer of finely ground cinnabar, whose brilliant red particles reflected light in a way that gave the surface a depth and luminosity that neither pigment could achieve alone. In some cases, a final translucent layer, possibly of wax or organic medium, was burnished to a high polish, creating a surface that almost seemed to glow from within. This layering technique, which art historians have termed the Pompeian finishing method, represents a level of sophistication in paint application that has no direct parallel in modern practice. The Roman painter understood, not theoretically but practically, how light interacts with layered pigment particles of different sizes and compositions. He understood that a coarse underlayer scatters light broadly, while a fine overlayer focuses and intensifies it. He understood that a translucent final coat traps light and creates an effect of luminous depth. These are principles that modern optical physics can explain, but the Roman painter did not derive them from physics. He derived them from painting, from centuries of trial, observation, and refinement within a guild tradition that transmitted its findings from master to apprentice. No Roman text describes this technique. No surviving manual explains the layering method, the specific grind required for each layer, the type of medium used for the final polish. The technique was recovered only by painstaking analysis of the surviving paint surfaces themselves, by working backward from the physical evidence to infer the process, and even so, modern conservators who have attempted to replicate the Pompeian finish have found it extraordinarily difficult to match. The variables are too many, the tolerance is too fine, the feedback loops between hand and eye too subtle to reconstruct from analysis alone. This is what it means to lose a craft tradition. It is not like losing a book, where the words are gone, but the language survives. It is like losing a language itself, not just the vocabulary and grammar, but the capacity to think in it, to feel in it, to perceive the world through its particular lens. A pigment tradition is a way of seeing. When it dies, a dimension of human experience goes with it. The African continent, often overlooked in discussions of ancient pigment technology, provides its own catalogue of losses. The ochre traditions of southern Africa, which stretch back further than any other documented pigment use on Earth, involved not merely the mining and grinding of iron-rich earth, but sophisticated heat treatment processes that transformed the colour and properties of the raw material. Archaeological studies at sites in Swaziland and South Africa have revealed that ancient peoples heated ochre to carefully controlled temperatures to shift its colour from yellow to red, a process that involves the thermal conversion of goethite to hematite, two different crystal forms of iron oxide. The temperatures required for this conversion, roughly 250 to 300 degrees, are moderate, but the control required to achieve a specific shade without overheating is significant. Different target temperatures produce different reds. Warm orangey reds at lower temperatures, cooler bluish reds at higher ones. The ancient practitioners clearly controlled this process with precision, as evidenced by the consistency of colours found at individual sites. Further north, in the medieval kingdoms of West Africa, a tradition of indigo dyeing developed that rivaled and perhaps surpassed the sophistication of any other textile dyeing tradition in the world. The Yoruba dyers of present-day Nigeria in particular developed techniques for achieving extraordinarily deep, intense blues through a process of repeated immersion and oxidation that could involve 20 or more separate dipping cycles, each followed by careful exposure to air. The resulting cloth, known as a dyer, displayed a depth and permanence of colour that astonished European traders when they first encountered it. The chemistry involves the reduction of indigo to its soluble leucoform in an alkaline vat, its absorption into the fibre, and its reoxidation to insoluble indigo within the fibre structure. The process is conceptually simple. The execution is not. The preparation of the vat alone, using wood ash, certain plant materials, and carefully controlled fermentation, required knowledge that took years to acquire and that was held within family lineages of dyers. Much of this knowledge survived into the 20th century, and fragments persist today. But the full depth of the tradition, the ability to produce the deepest, most light-fast blues, the knowledge of which plant varieties produced the strongest dye, the understanding of how seasonal and environmental factors affected the fermentation, has been severely eroded by the displacement of natural indigo by synthetic alternatives. The last masters who held the complete tradition are dying. Their children, facing economic pressures that make traditional dyeing unviable, are choosing other livelihoods. The flame flickers. To understand the full depth of what has been lost, it is necessary to look closely at the pigments themselves, not as abstract chemical formulas, but as the products of specific human hands in specific workshops on specific days that are now forever beyond our reach. The core problem is not merely that recipes are missing. It is that the kind of knowledge required to produce these pigments, tacit knowledge, embodied knowledge, the kind that lives in muscle memory and intuition and cannot be fully reduced to words, may be fundamentally unrecoverable. Begin with Tyrian Purple, because no pigment better illustrates the intersection of staggering effort, irreplaceable craft knowledge, and total loss. Tyrian Purple was not a pigment in the traditional sense. It was a dye, a colorant that chemically bonds to fabric fibers rather than sitting on a surface. Its source was biological. The hypobranchial gland of predatory sea snails belonging to the family Muricidae, primarily Balenus brandaris and Hexaplex trunculus. Each snail produces only a tiny quantity of the mucus from which the dye precursor is extracted. Estimates range from a fraction of a gram to roughly 1.5 grams per animal. To produce enough dye to colour a single garment, ancient dye makers needed thousands of snails. Some estimates for a full royal robe run as high as 250,000 individual animals. The scale of the ancient industry is visible in the archaeological record. At Sidon, in modern-day Lebanon, excavations have uncovered mounds of crushed murex shells meters deep and covering areas the size of city blocks. These are the waste heaps of centuries of dye production. Mountains of discarded shells, each one representing a single snail harvested, cracked open, and scraped for its precious glandular secretion. The Roman author Pliny described the stench of the dye works as almost unbearable, noting that the smell clung to everything and everyone in the vicinity. This was not a delicate craft practiced in clean workshops. It was a massive, reeking industrial process, and yet the dye it produced was sublime. Tyrian purple, at its finest, was a deep, rich colour that shifted between violet and crimson depending on the light. Unlike virtually every other ancient dye, it did not fade with washing or sun exposure. It actually improved, becoming richer and more luminous over time. This property, which no fully synthetic dye has ever replicated, was so prized that Tyrian purple became the most expensive colorant in the ancient world. Roman sumptuary laws restricted its use to the emperor and the highest ranks of the aristocracy. To wear purple without authorization was, at various points in Roman history, a capital offense. But here is the problem. The chemical compound responsible for Tyrian purple, 6,6-dibromo-indigo, was identified in the early 20th century. It can be synthesized in a laboratory. Modern chemists can produce the molecule, and the resulting color, while recognizably purple, does not match the ancient dye. The depth, the luminosity, the way it interacts with light on fabric. Something is different. The ancient descriptions consistently emphasize a quality of the dye that modern recreations do not achieve. The reason lies in the manufacturing process, and this is where the loss becomes most painful. The ancient process involved not just the extraction of the glandular secretion, but a complex series of steps: salting, soaking, slow heating in water or urine, exposure to sunlight, and a carefully controlled fermentation or reduction process that could take days or weeks. The exact conditions, temperature, pH, duration, the type of vessel used, whether the vats were open or sealed, the precise stage at which sunlight was introduced, varied between workshops and represented closely guarded trade secrets. Different combinations of Murex species, different fermentation times, and different reduction methods produced different shades, from reddish-violet to blue-violet. The most prized shade, the fabled twice-dyed Tyrian purple, involved 2 separate immersions in different dye baths, each prepared under different conditions. None of these process details survive in sufficient specificity to allow faithful reproduction. Pliny describes the general outlines, so does the 4th century compiler Julius Pollux, but their accounts are the descriptions of observers, not practitioners. They tell us what the process looked like, not what it felt like, not the subtle signs that told a master dye maker when the fermentation had reached the right stage, when the reduction was complete, when the moment to add the fabric had arrived. That knowledge was tactile, olfactory, intuitive. It was the kind of knowledge that took years to learn and could not be transmitted in a sentence. When the Phoenician dye industry finally collapsed, undermined by economic decline, the Arab conquests, and the eventual substitution of cheaper dyes, the last practitioners carried their knowledge into oblivion. The archaeological chemist Inga Buscan-Canold, who has spent decades attempting to recreate Tyrian purple using ancient methods, has described the process as a moving target. Each variable she adjusts reveals 3 more she had not considered: the snail species, the time of year of harvest, the freshness of the glandular extract, the mineral content of the local water supply. All of these affect the final color. The ancient dye makers controlled for all of these variables simultaneously through expertise accumulated over generations. Modern science, approaching the problem analytically, struggles to replicate what tradition maintained effortlessly. And it gets worse. Tyrian purple is at least a known quantity. We have the chemical formula, we have the source organism, we have fragmentary descriptions of the process. For many ancient pigments, we have far less. Consider the pigment known as dragon's blood. The name, which appears in texts spanning from ancient Rome to medieval Europe to traditional Chinese medicine, refers to a deep red resin, but the specific biological source of the ancient material is a matter of ongoing debate. The resin of the dracena tree, found in the Canary Islands, Yemen and Southeast Asia, produces one type of dragon's blood. The rattan palm Daemonerops, found in Indonesia, produces another. Ancient sources may refer to either, both, or neither. Some scholars have argued that the original dragon's blood was derived from an entirely different organism that has not been identified. The pigment appears in Roman-era recipes for varnishes and paints, in medieval illuminated manuscripts, and in traditional lacquerwork across Asia, but the specific preparation methods described in each tradition differ so substantially that it is unclear whether they are describing the same material. The name survived. The substance behind the name blurred into uncertainty. This blurring, where a pigment's name endures but its identity fractures, is one of the most insidious forms of knowledge loss. The ancient world did not have standardized chemical nomenclature. A color name like ochre or sinopia or minium might refer to different substances in different centuries, different regions, or different trades. When a medieval scribe copies a Roman recipe that calls for chrysocolla, he may understand the term to mean something entirely different from what the Roman author intended. The word survives, the reference shifts. Over centuries of copying and translation, the chain of meaning breaks. Modern scholars attempting to reconstruct ancient pigment recipes must navigate a landscape of synonyms, homonyms, and false cognates, words that look familiar but point to lost substances. The case of minium illustrates this perfectly. In Roman usage, minium originally referred to cinnabar, mercuric sulfide, a brilliant red mineral pigment. Over time, the word shifted to denote red lead tetroxide, a completely different chemical compound with a different color, different toxicity profile, and different production method. Both were red. Both were called minium. The confusion between the two persists in scholarly literature to this day, and it means that any ancient recipe calling for minium is inherently ambiguous. Was the author describing a mercury compound or a lead compound? The answer determines everything: the color, the preparation, the safety considerations. And in most cases, the answer is permanently uncertain. But here is what makes this truly terrifying. The problem is not limited to obscure or exotic pigments. Even for widely used, well-documented colors, the gap between ancient achievement and modern reproduction yawns wide. Consider vermilion, the synthetic form of mercuric sulfide, which was produced by combining mercury and sulfur and heating the mixture in a sealed vessel. The basic chemistry is straightforward. Modern vermilion can be produced in any competent laboratory. And yet, connoisseurs and conservators consistently note that the finest ancient and medieval vermilions possess a depth and warmth that modern versions lack. The art historian Daniel Thompson, in his landmark study, The Materials of Medieval Painting, observed that the best medieval vermilion was produced by a lengthy process of repeated sublimation and grinding that modern manufacturers abandoned in favor of faster, more economical methods. The ancient method was slower, more labor-intensive, and more wasteful of raw materials. It also produced a superior product. When efficiency replaced craftsmanship, quality was the casualty. This trade-off, efficiency versus quality, speed versus mastery, is a thread that runs through the entire history of pigment loss. The Industrial Revolution did not merely change how pigments were made, it changed what pigments were. The transition from hand-ground, workshop-produced pigments to factory-manufactured chemical colors in the 18th and 19th centuries represented a fundamental shift in the relationship between maker and material. In a traditional workshop, a pigment maker might spend days grinding a single batch of ultramarine, the precious blue pigment derived from lapis lazuli, adjusting the particle size through successive stages of washing and levigation to achieve the optimal balance of color intensity and transparency. The process was meditative, painstaking, and required a trained eye that could distinguish between dozens of slightly different grades of blue. In a factory, the same pigment was produced in bulk by standardized chemical processes that prioritized consistency and volume over subtlety and luminosity. The result, paradoxically, was a world with more color options but less color quality. The synthetic ultramarine, developed by the French chemist Jean-Baptiste Guimet in 1828, was a triumph of industrial chemistry, cheaper, more consistent, and more widely available than natural ultramarine. It was also, by the near-universal judgment of painters who had used both, a less beautiful blue. The depth, the subtle warmth, the almost internal glow of the finest natural ultramarine from the Sarisang mines in Afghanistan. These qualities were not replicated by the synthetic version. They were not even fully understood. They arose from the specific geological conditions under which the lapis lazuli formed, the specific impurities present in the mineral, the specific grinding and washing techniques used to extract the pigment, a chain of causation so complex and so contingent that industrial standardization could not capture it. The Roman natural historian and military commander Pliny the Elder, whose death during the eruption of Vesuvius in 79 of the Common Era robbed the world of one of its most encyclopedic minds, wrote extensively about pigments and their preparation. In one passage, he describes the manufacture of a particularly fine white lead pigment, explaining that the best examples came from Rhodes and were produced by a slow process involving vinegar vapors and lead sheets suspended in clay pots sealed for 30 days. His description is detailed enough to suggest a process that was well established and widely practiced. Modern attempts to follow his instructions have produced white lead of varying quality, some approaching the density and covering power of historical samples, others falling significantly short. The variable that researchers cannot control is time. Not the 30 days of the process, but the centuries of accumulated refinement that preceded the version Pliny described. He was recording the end product of a tradition. The tradition itself, the failed experiments, the incremental improvements, the insights gained and transmitted from generation to generation, is gone. There is a particular cruelty in this kind of loss. It is not the cruelty of fire or war or deliberate destruction. It is the cruelty of indifference. Nobody decided to destroy the knowledge of ancient pigment making. Nobody burned the recipes or banned the craftsmen. The knowledge simply became economically irrelevant. When cheaper alternatives became available, the old methods were abandoned. When the old methods were abandoned, the practitioners retired or died without successors. When the practitioners died, the knowledge they carried, the knowledge that lived in their hands and their eyes and their noses, evaporated as completely as if it had never existed. This is destruction by neglect. It is the quietest and most thorough form of forgetting, and the forgetting is cumulative. Each lost generation of craftsmen takes with it not just the explicit knowledge of recipes and processes, but the implicit knowledge of troubleshooting, the understanding of what to do when the kiln runs too hot, when the raw material is of unusual composition, when the weather or the humidity or some other environmental factor affects the outcome. This troubleshooting knowledge, which in any craft tradition represents the deepest and most valuable layer of expertise, is by its nature the hardest to record and the first to disappear. You can write down a recipe. You cannot write down the feel of the right consistency, the smell of the correct stage of fermentation, the instinct that tells a master to stop heating at precisely this moment. These things must be learned by doing, under the guidance of someone who already knows. When the chain of transmission breaks, they are gone, permanently. The modern pigment industry is, in a very real sense, a second attempt. Almost nothing in a modern paint tube connects directly to the ancient traditions. The materials, the methods, the tools, the knowledge base, all have been reinvented from scratch, using the entirely different approach of analytical chemistry rather than empirical craft, where ancient pigment makers worked forward, starting with raw materials and manipulating them through processes developed over generations until the desired color emerged. Modern chemists work backward, starting with a desired chemical formula and engineering a production process to achieve it. The two approaches produce superficially similar results, but the ancient approach, refined over millennia of human hands, sometimes achieved outcomes that the modern approach, for all its precision, cannot match. This is the core problem. Not that we lack the intelligence or the technology to produce ancient colours, but that the specific kind of knowledge required to produce them, knowledge that is procedural, embodied, contextual, and generational, is a kind of knowledge that our civilization has systematically devalued, and that, once lost, cannot be recovered through analysis alone. You can analyze a pigment, you can identify every atom in its structure, you can map its crystal lattice at the nanometer scale, and you can still fail to reproduce it, because knowing what something is made of is not the same as knowing how to make it. This distinction between analytical knowledge and procedural knowledge, between knowing that and knowing how, is the key that unlocks the entire mystery of lost pigments. It explains why a civilization with electron microscopes cannot match the output of craftsmen with clay kilns. It explains why the colours on ancient walls continue to humble the laboratories that study them. And it explains why the loss of these pigments is not merely an aesthetic misfortune, but an epistemological catastrophe, a demonstration that entire categories of human knowledge can vanish beyond recovery, leaving behind only the mute evidence of their former existence. The evidence stares back at us from every museum wall, every archaeological site, every conservator's report. Colour that should not have survived has survived. Colour that modern science should be able to reproduce remains stubbornly beyond reach. The ancient craftsman knew something we do not know, and the hardest truth of all is this: we may never know what it was. The frustration of this ignorance is compounded by the tantalizing near misses that punctuate the research. In 2004, a team of French and American chemists published a major study on Maya blue, in which they claimed to have finally replicated the ancient pigment by heating a mixture of indigo and palygorskite to 150 degrees. The resulting material was chemically similar to ancient samples and showed good stability. The team celebrated. The conservation community took notice, and then further analysis revealed discrepancies. The ancient Maya blue displayed a more uniform distribution of indigo molecules within the clay structure, a tighter bond at the molecular level, and a subtly different spectral profile. The modern recreation was closer than anyone had come before, but it was not identical. The last few percent of difference proved to be the hardest, and within that gap lies the ghost of a lost technique. Similar near misses characterize the study of Egyptian blue. Researchers at Stanford University and the Getty Conservation Institute have made significant advances in understanding the firing conditions required to produce calcium copper silicate. They have identified the optimal temperature range, the ideal ratio of raw materials, and the importance of a flux, a substance that lowers the melting point and facilitates the chemical reaction. Modern recreations can now produce Egyptian blue that is visually convincing to the naked eye, but spectroscopic analysis consistently reveals differences in crystallite size, in the distribution of trace impurities, and in the near-infrared fluorescence behavior that was one of the pigment's most distinctive properties. Ancient Egyptian blue emits near-infrared radiation when illuminated with visible light, a property so distinctive that it has been used by conservators to identify the pigment on artifacts where it is invisible to the naked eye, obscured by dirt or overpaint. Modern recreations fluoresce too, but the intensity and spectral profile differ. Something in the ancient process, perhaps the specific sand used, perhaps trace mineral impurities in the local copper ore, perhaps the thermal profile of an ancient Egyptian kiln with its characteristic draft patterns, produced a microstructure that modern ovens, with their precisely controlled and uniform temperatures, cannot replicate. The historian of science, Pamela Smith, who has devoted her career to the study of artisanal knowledge in early modern Europe, has written eloquently about this problem. In her view, the failure to reproduce ancient materials is not a failure of modern science, but a vindication of an older understanding of knowledge, one in which bodily skill, sensory perception, and iterative practice were recognized as forms of knowing in their own right, as rigorous and as valuable as theoretical understanding. The hand knows things the mind does not, Smith has written, and when the hand ceases to practice, those things are lost. This observation carries profound implications for the history of technology. We tend to think of technological progress as a story of ideas, of breakthroughs in understanding that lead to new capabilities. But the history of pigments suggests that many ancient technologies were not primarily the product of ideas at all. They were the product of practice, of generations of hands, repeating, refining, and slowly perfecting processes that were never fully understood in theoretical terms. The craftsman who produced the finest Egyptian blue may not have known that he was creating a calcium copper silicate crystal. He knew that this sand, from this riverbed, mixed with this copper ore, from this mine, heated in this kiln for this long, produced the best blue. His knowledge was hyperlocal, hyperspecific, and hyper-effective, and it was precisely this local specificity that made it so vulnerable. Because when the local conditions changed, when the mine was exhausted, the riverbed shifted, the kiln was destroyed, the recipe no longer worked, and no theoretical understanding existed to diagnose the problem. The Japanese concept of shokunin, sometimes translated as craftsmanship, but more accurately rendered as the spirit of the artisan, captures this idea with precision. A shokunin does not merely know how to make something. A shokunin has become the process, has internalized it so deeply that the distinction between maker and method dissolves. In pigment traditions that survived into the modern era, this level of integration between practitioner and practice is visible and measurable. Studies of traditional Indian miniature painters have shown that master artists can distinguish between pigment samples that differ in particle size by less than a micrometer, a discrimination far below the threshold of what is supposed to be possible for unaided human perception. They achieve this not through superhuman senses, but through decades of daily, intimate contact with their materials. Their fingers have learned what their eyes cannot see. When we lose a pigment tradition, we lose not just a recipe, but an entire ecology of embodied expertise, the accumulated sensory intelligence of generations, encoded in hands and eyes and noses that are now dust. No spectrometer can recover that. No archive can preserve it. It is the most perishable form of knowledge there is. And the modern world, with its emphasis on standardization, reproducibility, and written documentation, is structurally hostile to this kind of knowledge. If it cannot be written down, it is not considered real. If it cannot be quantified, it is not considered reliable. If it cannot be reproduced by a stranger, following written instructions, it is not considered knowledge at all. And so the traditions that sustained ancient pigment making for millennia, traditions that were, by any honest measure, extraordinarily effective, are dismissed as mere craft, as folklore, as pre-scientific fumbling. The colours on the walls tell a different story. They tell us that those pre-scientific craftsmen achieved results that our science cannot match. But we are not listening. We have forgotten how to hear what hands can say. There is one more dimension to this problem that demands attention before we move forward, because it reveals the depth of the crisis in its starkest form. Some lost pigments are not merely difficult to reproduce, they are dangerous to reproduce. And this dual nature, beauty intertwined with toxicity, has played a quiet but devastating role in the history of pigment loss. Lead tin yellow, one of the most important pigments in European painting from the 15th through the 18th centuries, was used by virtually every major artist of the Renaissance, from Jan van Eyck to Rembrandt. It produced a warm, opaque, brilliant yellow that was essential for depicting golden light, rich fabrics, and luminous flesh tones. Then, sometime in the mid-18th century, it disappeared. Not gradually, completely. For 200 years, no art historian, no conservateur, no chemist could identify the yellow pigment visible on the canvases of the old masters. It was as though the colour had never existed. The pigment was not rediscovered until 1941, when the German chemist Richard Jacobi identified lead tin yellow type 1 on paintings in the Munich Pinakothek. A second variant, lead tin yellow type 2, was identified later. The chemical compositions were established. The pigments could be synthesized. But here is what remains unexplained. No surviving text from the period of its use contains a clear, unambiguous recipe for producing lead tin yellow. Despite being one of the most widely used pigments in European art for 3 centuries, Its manufacturing process was never documented in any surviving workshop manual, treatise, or handbook. The artist who used it obtained it from pigment sellers. The pigment sellers obtained it from manufacturers. The manufacturers, and this is the crucial point, appear to have been glassmakers and ceramicists for whom lead tin yellow was a byproduct or subsidiary product of their primary craft, and who did not consider its preparation worth recording separately. When the glass-making traditions that incidentally produced lead tin yellow changed or died out, the pigment simply ceased to exist. Nobody noticed at the time because cheaper alternatives were available. It was only centuries later, when scholars began examining old paintings with modern instruments, that the absence was detected. Gone. Permanently, at least in its original form. Modern syntheses can produce lead tin yellow, but the exact conditions used by Renaissance-era glass workshops, with their particular furnace designs, particular raw material sources, and particular firing schedules are not known. The resulting modern pigment is chemically correct, but may differ in subtle ways: particle morphology, trace impurities, optical behavior from the historical material. We will never know for certain, because we cannot compare our modern product to a freshly made historical sample. Only aged historical samples survive, and aging changes things. Verdigris, the brilliant blue-green pigment produced by the corrosion of copper in the presence of acetic acid, tells a related story. The basic chemistry is simple. Expose copper plates to vinegar fumes, scrape off the resulting green crust, and grind it into a pigment. Medieval and Renaissance texts describe this process in reasonable detail, and modern recreations are possible. But the verdigris found on medieval paintings has proven remarkably more stable than modern versions, which tend to darken and become transparent over time. Something about the medieval preparation, perhaps the specific type of vinegar used, perhaps the duration and conditions of the corrosion process, perhaps the binding medium in which the pigment was suspended, produced a more durable product. The art conservator Murex Spring, working at the National Gallery in London, has spent years analysing medieval verdigris and has concluded that the best examples were prepared using methods significantly more complex than the simple recipes found in surviving texts. The texts, once again, recorded only the outline. The critical details lived in the workshop, and perhaps the most haunting example of all is the pigment known as mummy brown. From the 16th through the 19th centuries, European painters used a brown pigment literally manufactured from the ground-up remains of Egyptian mummies, both human and feline. The bitumen and resins used in the embalming process, combined with the desiccated organic material, produced a warm, transparent brown prized for glazing and shadows. The pre-Raphaelite painter Edward Burne-Jones, upon learning the true source of his mummy brown pigment in the 1880s, was reportedly so horrified that he gave his tube a ceremonial burial in his garden. By the early 20th century, the supply of available mummies had dwindled, and the pigment gradually disappeared from commerce. Mummy brown is unique among lost pigments because its loss is, by any humane standard, a good thing. Nobody mourns the end of grinding up human remains for paint, but the case illustrates a broader principle: that ancient pigments existed within cultural and economic contexts that are as impossible to reproduce as the chemical processes themselves. The availability of certain raw materials, the existence of specific trade networks, the cultural acceptance of certain practices, these were all preconditions for the pigments they sustained. When the context changed, the pigment changed or disappeared, regardless of whether the chemical knowledge survived. This point applies far beyond the macabre example of mummy brown. Lapis lazuli, the source of natural ultramarine, was for centuries mined primarily from a single source, the remote Sari-Sang mines in Badakhshan in present-day Afghanistan. The stone travelled overland through Central Asia to the Mediterranean, a journey of thousands of miles that could take months. The cost of the raw material, by the time it reached a European artist's workshop, was often greater per weight than gold. This extreme cost drove the development of an elaborate processing method, described in detail by the 15th century artist Cennino Cennini, designed to extract the maximum amount of high-quality pigment from each precious lump of stone. Cennini's method involved kneading the ground lapis into a paste of melted wax, pine resin, and gum mastic, then washing this paste repeatedly in lye water to coax out the blue particles while leaving behind the grey impurities. The process could take days and required extraordinary patience. Cennini's description is one of the most detailed ancient pigment recipes to survive, and it has been replicated by modern researchers with considerable success. And yet, even here, the modern product does not perfectly match the finest historical examples. The best medieval ultramarine has a depth and warmth that modern recreations, even those using the same method and the same Afghan lapis, do not achieve. One possibility is that the mineral composition of the lapis lazuli itself has changed, that the best veins, those richest in the lazurite mineral that produces the blue color, were mined out centuries ago, and the remaining stone is of lower quality. Another possibility is that the grinding and washing techniques, which Cennini describes in general terms, involved subtleties of timing and handling that his text does not capture. The most likely answer is that both factors apply. The loss is double. The finest raw material is gone, and the finest techniques for processing it are gone. What remains is an approximation. But the real question is not what burned, it is what we will never know existed. For every lost pigment that has been identified by modern analysis, how many others existed that left no surviving trace? Pigments applied to organic materials, to textiles, to paper, to wood, are far less likely to survive than those applied to stone or plaster. The entire colour world of ancient textiles, of painted banners and dyed fabrics and illuminated scrolls that were not stored under ideal conditions, is almost completely gone. We see the pigments that survived on the most durable surfaces. We can only imagine the pigments that adorned the perishable ones, and so the core problem stands. We are a civilization that can photograph a black hole, sequence a human genome, and split an atom, but we cannot reproduce the blue on an Egyptian coffin or the red on a Roman wall. The knowledge we lack is not the kind that comes from intelligence or funding or technology. It is the kind that comes from doing something every day for a lifetime and teaching it to someone who will do the same. It is the kind of knowledge that our civilization has decided is not worth preserving. The walls disagree. The story of lost pigments would be merely sad if it ended with absence, but it does not end there. Across the world, in university laboratories, conservation studios, and the workshops of a handful of surviving traditional craftspeople, the effort to recover what was lost continues. Each lost pigment is its own mystery, its own investigation, its own confrontation between the power of modern science and the humility of realizing that power has limits. What follows are 5 such investigations, 5 colors that the ancient world mastered and the modern world is still struggling to understand. The first is Han Purple. In 1992, a physicist at Stanford University named Srinivasan Raghavan was conducting experiments with an esoteric quantum phenomenon called a Bose-Einstein condensate, a state of matter that occurs at temperatures near absolute zero, in which individual atoms lose their separate identities and begin behaving as a single quantum entity. During his research, he happened to examine the magnetic properties of a sample of Han Purple, the barium copper silicate pigment produced in China more than 2,000 years ago. What he found made him stop and reread his instruments. Han Purple, when cooled to near absolute zero, exhibited a phenomenon that Raghavan had never observed in any other material. The 3-dimensional magnetic behavior of its copper atoms collapsed into a 2-dimensional state. The magnetic interactions, which normally operate in all 3 spatial dimensions, suddenly confined themselves to a single flat plane. In the language of quantum physics, a spatial dimension had effectively disappeared. The material was exhibiting a macroscopic quantum effect at a scale visible to instruments, a behavior so unusual that Raghavan's initial paper on the subject, published several years later, was met with skepticism by portions of the physics community. The discovery had nothing to do with pigment manufacture. It was pure physics, but it raised a question that no one could answer. How did ancient Chinese craftsmen, working with technology that should not have been capable of producing barium copper silicates, create a material whose quantum properties are still yielding surprises to 21st century physics? The manufacture of Han purple requires barium, copper, and silica heated to temperatures exceeding 1000 degrees in a carefully controlled atmosphere. Barium minerals are uncommon and were not used in any other known Chinese craft tradition of the period. Copper and silica were more readily available, but the specific stoichiometric ratio required to form the barium-copper silicate crystal structure, rather than an amorphous glass or some other compound, implies a degree of chemical precision that should not have been achievable through trial and error alone. And yet, no evidence exists for a theoretical framework that could have guided the development. No Chinese text of the Warring States period or the Han dynasty describes the chemistry of pigment manufacture in anything approaching theoretical terms. The archaeologist Mark Pollard and his colleagues at Oxford University have proposed that Han purple may have developed as a byproduct of Chinese jade glass production. That craftsmen experimenting with barium-containing minerals for glass-making accidentally discovered that certain compositions, when fired under certain conditions, produced a striking purple rather than a transparent glass. This is plausible but unproven. The truth is that we do not know how Han purple was invented, how its manufacture was refined, or why it ceased to be produced sometime during the first centuries of the Common Era. Modern recreations exist. They are chemically identical to ancient samples. But the journey from raw materials to finished pigment, the sequence of discoveries, failures, and refinements that constitutes the real invention, is permanently beyond recovery. The strangeness deepens when you consider the distribution of Han purple in the archaeological record. The pigment appears on objects spanning roughly 500 years, from the 5th century before the Common Era to the 2nd century of the Common Era. During that period, its use was apparently restricted to high-status objects. The painted terracotta warriors of the first emperor's tomb, ritual bronze vessels, lacquerwork associated with the imperial court. It was not a common pigment. It was not available to ordinary painters or craftsmen. It was a state secret, or something close to one, a technology controlled by the imperial workshops and distributed only to authorized artisans. This restriction may have sealed its fate. When pigment knowledge is widely distributed, held by thousands of workshops across a broad geographical area, it is resilient. The loss of any one workshop does not endanger the tradition as a whole. But when knowledge is concentrated, held by a small number of specialists operating under state patronage, it is catastrophically vulnerable. The end of patronage means the end of the craft. There is no broader community to sustain it, no market to demand it, no independent tradition to carry it forward. The craftsmen have no alternative employer. Their skills have no alternative application. They simply stop, and their children learn something else. The physicist Ian Freestone, who has studied the production technology of ancient glass and pigments for decades, has observed that Han purple represents one of the clearest examples in the archaeological record of a sophisticated technology that arose, flourished, and disappeared entirely within a circumscribed period, leaving no successor tradition and no documented process. It is as though someone invented a new material, used it for 5 centuries, and then uninvented it. Freestone has written, "That should not happen." But it did. But here is the problem. Han purple's story does not end with its chemistry. The pigment was not merely decorative. It appears on terracotta warriors, on bronze vessels, on ritual objects associated with the Chinese imperial court. Its production required rare and expensive raw materials, high-energy kilns, and specialized knowledge. It was, in every sense, a prestige material, a technology associated with power. When the political and economic structures that sustained its production changed, the pigment was among the first casualties. The craftsmen who made it worked for the state. When the state no longer required their product, they had no market, no patronage, no reason to train the next generation. The knowledge died not because it was forbidden or destroyed, but because nobody was paying for it anymore. The second investigation concerns a pigment that is, by any measure, the most chemically bizarre in the ancient world, Maya blue. The story of Maya blue's modern rediscovery begins in 1931, when the American archaeologist H.E.D. Pollock noticed that certain blue-painted surfaces at the Maya site of Chichen Itza displayed an unusual resistance to chemical solvents. Most pigments, when swabbed with acids or alkalis, yield at least traces of dissolved color. Maya blue did not. Pollock noted the anomaly and moved on. It was not until the 1960s that the mineralogist Rutherford John Gettens and the chemist George Stout conducted the first systematic chemical analysis of the pigment and made a startling discovery. Maya blue contained indigo, an organic plant dye, embedded within the crystal structure of a clay mineral called palygorskite. This should not work. Organic dyes are inherently fugitive. They decompose when exposed to light, air, moisture, or biological agents. That is why most ancient organic colorants have vanished entirely. The brilliant yellows of Roman textiles, the greens of medieval illuminated manuscripts, the pinks and mauves of classical Greek wall paintings, all have faded to ghostly traces or disappeared altogether. Organic dyes are chemistry's mayflies, brilliant and brief. For an organic dye to survive 1,000 years of tropical exposure is not unusual. It is, in conventional chemical terms, impossible, and yet Maya blue exists. It survives on temple walls at Chichen Itza, on ceramic vessels recovered from the sacred cenote, on murals at Bonampak and Cacaxtla. It survives because the Maya found a way to do something that modern materials science did not conceptualize until the late 20th century. They created a host-guest compound in which the organic indigo molecules are physically trapped inside the nanoscale tunnels of the palygorskite clay crystal. Once inside, the indigo is shielded from every chemical and biological agent that would normally destroy it. The clay acts as an inorganic prison for an organic molecule, and the combination is more stable than either component alone. The math is striking. Palygorskite contains channels approximately 3.7 by 6.4 angstroms in cross-section. Indigo molecules are approximately 4.8 by 12 angstroms. They should not fit, and yet spectroscopic evidence confirms that indigo molecules do enter the channels, likely undergoing a conformational change, a physical bending or flattening that allows them to squeeze in. Once inside, they form hydrogen bonds with the interior surface of the channel, locking them in place. Modern attempts to reproduce this process have achieved partial success. The method is conceptually straightforward. Mix powdered palygorskite with indigo, heat the mixture, and hope the molecules migrate into the channels. The chemist Constantino Reyes Valerio, working in Mexico in the 1990s, demonstrated that heating a mixture of indigo and palygorskite to moderate temperatures in the presence of copal incense, a tree resin that the Maya used in religious ceremonies, produced a pigment closely resembling ancient Maya blue. His work suggested that the pigment might have been produced during ritual ceremonies, combining practical chemistry with spiritual practice in a way that had no parallel in the Western tradition. This idea was expanded by the archaeologist Dean Arnold, who argued that the production of Maya blue was inseparable from the ritual context in which it was used. The pigment appears most frequently on objects associated with sacrifice and offerings to Chak, the rain god. Arnold proposed that the heating of indigo and palygorskite took place over the same ceremonial fires used for burning copal incense, and that the pigment was therefore literally a product of prayer. If Arnold is correct, then the loss of Maya blue was not merely a technical loss, it was a spiritual one. The knowledge of how to make the pigment was embedded in a religious practice that ceased when the civilization that practiced it collapsed. No written Maya recipe for the pigment has ever been found. The oral tradition that may have sustained its production is silent. What remains is the color itself, brilliant, defiant, and unreproducible in its full ancient form. And the implications of Maya blue extend far beyond the history of pigments. If the Maya were producing nanocomposite materials through empirical craft knowledge, without any theoretical framework for nanoscience, then the question of what else they knew and what else they made becomes urgent and unsettling. Were there other host-guest compounds, other nano-engineered materials produced by ancient civilizations and lost when those civilizations fell? The answer is almost certainly yes, and the evidence is almost certainly gone, destroyed by time, climate, and the perishability of the surfaces on which those materials were applied. The archaeochemist Dominique Cardon, in her monumental survey Natural Dyes, Sources, Tradition, Technology and Science, has documented hundreds of dyeing traditions from around the world, many of which involve chemical processes that, when analysed in modern terms, reveal surprising sophistication. Fermentation vats that function as bioreactors, mordanting processes that exploit coordination chemistry, multi-step extraction procedures that would not be out of place in a modern organic chemistry laboratory. In each case, the practitioners achieved their results through empirical tradition, not theoretical understanding. And in most cases, the full depth of those traditions has been lost to the contraction of traditional craft in the face of industrial competition. Maya blue stands as the most dramatic example of this phenomenon. It is a material that should not exist according to the assumptions we bring to ancient technology. It is a material that we cannot fully reproduce, despite knowing exactly what it is made of. And it is a material whose production was embedded in a cultural and spiritual context that is as irrecoverable as the chemistry itself. The pigment was not just mixed, it was prayed into existence. And that prayer, that combination of technical skill, ritual knowledge, and spiritual intention, is as lost as the civilization that practiced it. The third mystery is one that has humbled every chemist who has approached it: the Pompeian red wall finish. The term covers a range of red finishes found in Roman domestic architecture, but the most celebrated examples come from the Villa of the Mysteries at Pompeii, where an extraordinary cycle of wall paintings depicts scenes of initiation into the cult of Dionysus. The reds in these paintings are not merely well preserved, they are vivid, almost shockingly so, as though they had been painted recently rather than nearly 2,000 years ago. Art conservators who have studied the walls describe a luminous quality, a sense of light coming from within the paint surface, that modern pigments cannot achieve. As discussed earlier, the technique involved multiple layers of pigment applied with sophisticated understanding of how light interacts with stratified coloured particles. But what has resisted explanation is the final step: the polishing or burnishing of the surface, which transformed the painted wall from a matte, opaque surface into something approaching the luster of polished stone. The Roman architect Vitruvius describes this finishing process, noting that walls should be polished with a smooth stone or a piece of cloth until they achieve a mirror-like sheen. Modern conservators have attempted to replicate this finish and have found that it requires not just burnishing, but a very specific combination of plaster composition, plaster moisture level at the time of painting, pigment particle size, and bonding medium. Get any one of these variables wrong, and the burnishing either fails to produce a polish or damages the paint surface. The Italian conservator Paolo Mora, who devoted much of his career to the study of Roman wall painting technique, concluded after decades of experimentation that the Pompeian finish was the product of a highly developed craft tradition in which plasterers and painters worked in close coordination, each stage of the process being timed to coincide with the precise moisture state of the preceding layer. The plasterer had to know when the plaster was wet enough to accept paint, but dry enough to hold its shape. The painter had to know when to apply each pigment layer and when to begin burnishing. The margin for error was measured in minutes. The entire process, from initial plaster application to final polish, had to be completed within a single working session, because once the plaster set, no further modification was possible. This technique, painting on fresh, wet plaster, known as buon fresco, survived into the Renaissance and beyond. But the specific Roman variant, with its multiple pigment layers and high-gloss finish, did not. Renaissance fresco painters achieved extraordinary results using related but distinct methods. The Roman technique itself, with its particular demands on plaster composition, timing, and finishing, was lost during the upheavals of late antiquity and the early medieval period. What survives at Pompeii is a time capsule, a snapshot of a technique at its peak, frozen by the same catastrophe that killed its practitioners. There is a bitter irony in this. The eruption of Vesuvius, which destroyed the city and killed thousands, was also the event that preserved the wall paintings in a state of extraordinary completeness. Without the volcanic ash that sealed the walls from the atmosphere for nearly 2 millennia, The pigments would have weathered, the plaster would have crumbled, and the evidence of Roman painting technique would have been as fragmentary as the evidence from other Roman cities. Pompeii's destruction was also its preservation. The catastrophe that ended the lives of the painters also immortalized their work. We owe our knowledge of Roman wall painting to the same volcano that silenced the hands that created it. And what those hands created was, by any technical standard, extraordinary. Recent analyses using synchrotron radiation, X-rays produced by particle accelerators, have revealed details of the Pompeian paint layers that were invisible to earlier analytical methods. The cinnabar particles in the upper red layers show a remarkably narrow size distribution, suggesting that the Roman pigment grinders had developed methods for sieving or settling particle to select a specific size range. Larger particles reflect more light and appear brighter. Smaller particles are more transparent and allow underlying layers to show through. By controlling particle size, the Roman painters controlled the optical behavior of their paint at a level of precision that modern industrial pigment manufacturers only achieved in the 20th century. The conservation scientist Heinz Becker, who has studied ancient pigments at the Swiss Federal Institute of Technology, has described the Roman approach to wall painting as applied optics centuries before the invention of optical science. The Romans did not understand why their techniques worked. They did not know about particle scattering, about the relationship between grain size and reflectance, about the physics of light interacting with stratified colored media. They knew that this process, done in this order, with these materials prepared in this way, produced this result. And that was enough. Until it was not. Until the tradition that carried that knowledge ran out of carriers. The fourth lost colour is one that tormented European painters for centuries. A truly stable, brilliant green. The green problem plagued Western painting from antiquity through the early modern period. Unlike reds, blues, and yellows, for which stable and vivid pigments were available, green pigments were notoriously unreliable. Verdigris, the copper acetate pigment discussed earlier, was brilliant when fresh, but tended to darken and become transparent with age. Green earth, a natural iron silicate mineral, was stable but dull, useful for underpainting but inadequate as a final colour. Mixtures of blue and yellow pigments could produce green, but these mixtures often separated or shifted in colour as the individual pigments aged at different rates. The ancient Egyptians appear to have solved the green problem with a copper-based pigment closely related to Egyptian blue, but produced under different conditions. A green variant sometimes called Egyptian green. This material, a copper calcium silicate with a different crystal structure from its blue cousin, has been identified on Egyptian artifacts spanning more than 2 millennia. It is stable, brilliant, and weather-resistant. And like Egyptian blue, its exact manufacturing conditions have proven difficult to replicate. Modern recreations tend to produce a mixture of green and blue phases rather than a pure green, suggesting that the ancient process involved temperature controls or raw material selections that we have not yet identified. In China, a different solution was found. The Han Dynasty saw the production of a green pigment based on malachite, a naturally occurring copper carbonate mineral that was ground to specific particle sizes to achieve particular shades. The Chinese pigment makers discovered what modern color scientists have confirmed, that the perceived color of a ground mineral depends critically on particle size. Coarse malachite particles appear dark green. Fine particles appear pale, almost pastel green. By controlling the grinding process, Chinese artists could produce a range of greens from a single mineral source. The knowledge of how to achieve specific particle size distributions through grinding and levigation was a closely held craft skill, and it survived in the Japanese Iwa-enogu tradition described earlier. But in China itself, the tradition contracted severely during the political upheavals of the 19th and 20th centuries. Many grades of traditionally prepared malachite green are no longer available, and the craftspeople who could produce them have died without successors. And it gets stranger. In the Americas, a green pigment tradition developed along entirely independent lines. The Maya, in addition to their famous blue, produced green pigments by combining indigo with locally available yellow clays, creating mixtures that ranged from turquoise to deep forest green. But the most intriguing Mesoamerican green was not a pigment at all. It was a surface treatment. The jade workers of the Olmec and Maya civilizations developed techniques for polishing jadeite to a degree of perfection that made the stone's natural green color glow with an inner light. The polishing methods, which involved progressively finer abrasives culminating in substances whose identity is still debated, produced surfaces so smooth that modern scanning electron microscopy reveals tool marks at the nanoscale, scratches measured in billionths of a meter. The Mesoamerican polishers were, without knowing it, doing nanotechnology on stone. The techniques died with their civilizations. Modern lapidaries can achieve comparable results using diamond grit and powered equipment, but the ancient methods, which used only hand tools and natural abrasives, remain unmatched for their efficiency and the quality of the final surface. The green problem eventually found a partial solution in Europe through an unlikely route: the discovery of chromium. Chrome oxide green, first produced in the early 19th century, provided a stable, brilliant green that filled the gap left by centuries of unreliable copper-based alternatives. But chrome oxide green is opaque and heavy, a very different material from the luminous, semi-transparent greens that ancient painters achieved through careful particle size control of malachite, or through layered applications of blue and yellow pigments. The modern green solved the stability problem but sacrificed the subtlety. It was an engineering compromise, not a craft achievement, and the particular quality of green light that radiated from a carefully prepared malachite pigment, a quality described by traditional Japanese painters as the green of deep water, has no modern equivalent. The loss of green pigment traditions carries a particular poignancy because green is the color most closely associated with the natural world, with vegetation, growth, renewal, that the ancient world could produce greens of extraordinary beauty and permanence, while the modern world, surrounded by synthetic alternatives, cannot match them, is a small irony that speaks to the larger paradox of progress. We have gained efficiency, we have lost mastery, and the forest green on an 800-year-old Chinese scroll, still vivid, still luminous, still bearing the invisible fingerprints of the craftsman who ground it, asks a question that we cannot answer. What was it like to know your materials so intimately that you could hear them speaking to your hands? The fifth and final lost pigment tradition is perhaps the most poignant of all, because it was lost not in antiquity but within living memory: the tradition of Indian yellow. Indian yellow, known in Hindi as puri, was a luminous, transparent golden yellow used in Indian miniature painting, and, after its introduction to Europe in the 18th century, by Western artists including the landscape painter J. M. W. Turner. The pigment appeared in European catalogues as puri or Indian yellow, and its source remained mysterious for decades. European chemists analysed it and identified its principal component as the magnesium salt of euanthic acid. But where did euanthic acid come from? The answer, when it was finally confirmed in the late 19th century, was both mundane and extraordinary. Indian yellow was produced from the urine of cows that had been fed exclusively on mango leaves. The cows metabolized compounds in the mango leaves, excreting a bright yellow urine that was collected, heated to evaporate the water, and formed into balls of concentrated pigment. The process was practiced primarily in the rural area around Mongher in the Bihar region of India, where a small number of families maintained herds of cattle for this specific purpose. The pigment was extraordinary. Its transparency, its warmth, its luminous golden glow made it irreplaceable for certain effects in both Indian and European painting. The Turner scholar Joyce Townsend has identified Indian yellow in several of Turner's most famous works, noting that no other pigment available at the time could have achieved the same quality of light. But the process that produced it was troubling. Feeding cows exclusively on mango leaves, a diet lacking in essential nutrients, caused the animals considerable suffering. They became malnourished, weakened, and often ill. When the practice came to the attention of British colonial authorities in the early 20th century, it was prohibited on grounds of animal cruelty. The last confirmed production of genuine Indian yellow dates to approximately 1908. The ban was humane. It was also, from the perspective of pigment history, a final severance. Modern synthetic alternatives to Indian yellow exist. They approximate the color. They do not match the pigment's unique combination of transparency, warmth, and luminous depth. Painters who have used surviving stocks of historical Indian yellow describe a quality of light that no synthetic substitute reproduces. The pigment's unique optical properties arose from its specific chemical composition, the magnesium euanthate crystal, with its particular refractive index and light absorption profile, and from the particle characteristics produced by the traditional evaporation process. Synthetic euanthic acid can be produced in a laboratory, but the precise conditions of bovine metabolism, mango leaf chemistry, and traditional processing that produced the historical pigment constitute a system too complex and too ethically fraught to replicate. Indian yellow is gone, not because the knowledge was lost to fire or war or civilizational collapse, but because the knowledge, when fully understood, proved inseparable from a practice that a more compassionate age could not accept. The color was beautiful, the cost was cruelty, and so we chose, rightly, to let it go. But the loss is real, and the absence is visible on every palette that once held a ball of purity. The case of Indian yellow forces us to confront an uncomfortable question that the other lost pigments do not raise. Are some forms of knowledge better lost? Is there a point at which the beauty of the product does not justify the suffering of the process? For Indian yellow, the answer is clear, but the question resonates beyond this single pigment. Many ancient pigments involved materials and processes that would be unacceptable by modern ethical or environmental standards. The mining of cinnabar exposed workers to mercury poisoning. The production of lead white, the most important white pigment in European painting for 2 millennia, caused severe and often fatal lead poisoning among the workers who manufactured it. The harvesting of Murex snails for Tyrian Purple devastated marine ecosystems along the Phoenician coast. The mummy brown trade desecrated human remains. These are not comfortable facts. They complete the narrative of noble loss and tragic forgetting. The truth is that the ancient color world was built, in part, on suffering, on the exploitation of laborers, animals, and environments in ways that no modern society should wish to replicate. The loss of these pigments is, in some cases, a gain in human dignity. The challenge is to honor the technical achievement while acknowledging the human cost. To grieve for the knowledge while being grateful that some of the practices it sustained are gone. But even this nuanced position does not diminish the central mystery. The achievement remains extraordinary. The failure to reproduce it remains humbling. And the gap between what was known and what is known, between the craftsman's hand and the chemist's formula, remains as wide and as troubling as ever. There is one more dimension to the story of these 5 lost pigments that deserves attention, because it points to something fundamental about how knowledge is structured. In each case, Han purple, Maya blue, Pompeian red, the ancient greens, Indian yellow, the lost knowledge was not a single fact or a single formula. It was a system of raw material selection, processing, application, and evaluation, each stage depending on the others, each stage informed by generations of accumulated experience. Pull one element out of the system, and the whole thing collapses. Change the raw material source, and the processing parameters no longer work. Change the processing method, and the application technique no longer produces the right result. Change the application technique, and the evaluation criteria no longer apply. This systemic nature of craft knowledge is what makes it so difficult to reconstruct from analytical evidence alone. Modern science is reductionist. It works by breaking complex systems into simpler components and studying each one in isolation. But craft knowledge is holistic. It works by maintaining the integrity of the entire system, and it fails when any part of that system is disrupted. The two approaches are not incompatible, but they are different, and the difference explains why the most powerful analytical tools in the world cannot reverse engineer the products of the most traditional workshops in history. These 5 investigations, Han purple, Maya blue, Pompeian red, the ancient greens, and Indian yellow, share a common lesson. In each case, modern science has achieved partial understanding. In no case has it achieved complete reproduction. The gap between what we know and what the ancient craftsmen knew is not a gap of intelligence or technology. It is a gap of experience, of the accumulated, embodied, generational expertise that no instrument can measure and no database can store. That expertise was the real pigment. The colour on the wall is only its shadow. There is a room in the Louvre, climate-controlled and carefully lit, where a collection of Egyptian funerary objects rests behind glass. Among them is a small wooden chest, painted in the middle of the second millennium before the Common Era, decorated with scenes of the afterlife in blue, red, green, yellow, and black. The chest is not famous. It is not considered a masterpiece. Thousands of visitors pass it every day without stopping. But if you stand before it and look, really look, at the blue that edges the hieroglyphs on its side, you are looking at a colour that has not changed in approximately 3,400 years. The blue is as vivid today as it was when the painter set down his brush. The wood has darkened, the gilding has tarnished. The organic glues and binders have long since deteriorated, but the blue remains, perfect, undiminished, indifferent to time. Let that sink in. 3,400 years, that is longer than the entire history of Christianity, longer than the span between the founding of Rome and the present day, longer than any nation now existing has existed. The pigment on that chest has outlasted every institution, every language, every political system that has risen and fallen in the interim. Empires have been born and died in the time that blue has sat unchanged on a wooden box in a tomb in the desert, and we cannot make it, not exactly, not with the specific depth, uniformity, and luminous stability of the original. We can come close. We can produce something that passes a casual visual inspection. But when the spectroscopes and electron microscopes do their work, the differences emerge in crystal structure, in particle distribution, in fluorescence behavior. The ancient blue is not just old, it is better. The deeper truth that the history of lost pigments reveals is not about chemistry. It is about the nature of knowledge itself. We have built a civilization that is extraordinarily good at one type of knowledge, explicit, theoretical, transmissible knowledge that can be written in equations, stored in databases, and taught in classrooms. This is the knowledge that put a person on the moon, that sequenced the genome, that connected the world through fiber optic cables. It is powerful beyond any ancient craftsman's wildest imagination. But there is another type of knowledge, tacit, embodied, experiential, that our civilization is not merely bad at preserving, but is actively, structurally destroying. Every time a traditional craft dies, every time a workshop closes, every time the last practitioner of an ancient technique passes away without a successor, a thread of human knowledge is severed that can never be reteed. Not because we lack the will, but because the knowledge itself exists in a form that cannot be captured by our tools of preservation. You cannot upload muscle memory to a cloud server. You cannot store intuition on a hard drive. You cannot back up the sensory discrimination that allows a Japanese pigment maker to distinguish between particle sizes that no instrument in his workshop can measure. This is not science fiction. This is happening now today, at an accelerating pace. The number of traditional craft practitioners in every field, textiles, ceramics, metallurgy, pigment making, woodworking, stone carving, is declining worldwide. UNESCO maintains a list of intangible cultural heritage traditions that it considers to be in danger of extinction. The list grows longer every year. Each entry represents not just a cultural practice, but a body of embodied knowledge, knowledge about materials, about processes, about the physical world, that took centuries or millennia to develop, and that, once gone, is gone forever. In Oaxaca, Mexico, the tradition of producing natural cochineal dye, a brilliant red extracted from scale insects that feed on prickly pear cactus, persists in a handful of villages, maintained by families who have practiced the craft for generations. The cochineal tradition is one of the few ancient dye technologies that survived the transition to industrial chemistry, partly because the specific shade of red it produces has no exact synthetic equivalent, but the practitioners are aging, and the economic incentives to continue the laborious process of cultivating insects, Harvesting them, drying them, and extracting the dye are diminishing with each generation. The knowledge of which cactus varieties produce the healthiest insect populations, which harvest timing yields the strongest dye concentration, which processing methods produce the most light-fast color. This knowledge, honed over centuries, is held by a shrinking number of elderly specialists. In Afghanistan, the Sarasang lapis lazuli mines, the same mines that supplied the ultramarine pigment of the Renaissance, continue to operate, but under conditions of conflict and instability that have disrupted the traditional mining and processing knowledge that once sustained the finest grades of the stone. The master miners who knew which veins produced the richest lazurite, who understood the geology of the deposit in ways that no written survey could capture, have been displaced by decades of war. The stone is still mined. The knowledge of how to select the best material from a complex and variable deposit is being lost. In India, the tradition of natural indigo dyeing, once the foundation of an industry so vast that it shaped the colonial history of the subcontinent, survives in scattered communities, each holding fragments of a tradition that was once comprehensive. The complete process of indigo cultivation, extraction, vat preparation, and dyeing involved knowledge that spanned botany, microbiology, chemistry, and textile craft. No single surviving practitioner holds all of this knowledge. Each community retains a piece. The whole is no longer assembled in any one place, any one person, any one living tradition. The philosopher Michael Polanyi, writing in the 1960s, coined the term tacit knowledge to describe this category of knowing, knowledge that we possess and use but cannot fully articulate. His famous formulation, "We know more than we can tell," has become a cliché, but its implications are radical. If Polanyi is right, and the evidence of lost pigment suggests overwhelmingly that he is, then the total stock of human knowledge is not what is written in our books and stored in our databases. It includes everything held in human hands and human senses and human habits, and it is hemorrhaging at a rate that no library, no archive, no digital preservation effort can stanch. Let that sink in. The knowledge we can measure is growing exponentially. The knowledge we cannot measure is shrinking, and we have no way of knowing how much has already been lost, because tacit knowledge, by definition, leaves no inventory of its own absence. When the last Roman pigment maker died, no one wrote down that a body of knowledge had just vanished. When the last Maya priest, who knew how to combine indigo and palygorskite, passed away, no chronicle recorded the event. The knowledge simply ceased to exist, and the world continued, slightly diminished, without noticing. The modern world's relationship with colour illuminates this dynamic with painful clarity. We live in an age of unprecedented chromatic abundance. Digital screens can display millions of distinct colours. Industrial pigment manufacturers produce thousands of standardized colorants for every conceivable application. The palette available to a modern painter, a modern designer, or a modern architect is vastly larger than anything available to any civilization in history. And yet, the colors we produce are, by and large, less durable, less luminous, and less materially rich than the colors produced by ancient craftspeople working with a fraction of our resources. Modern paint fades, modern dye runs. Modern color, in its physical manifestation, is optimized for cost, consistency, and volume, not for beauty, durability, or depth. The oldest surviving examples of ancient pigment are still vibrant after millennia. The paint on a modern building begins to chalking within decades. The dye in a modern garment fades after a few hundred washes. We have more color than any civilization in history, and less relationship with it. We live in a world saturated with hue and starved of substance. The scholar and conservator Spike Bucklow, in his study of the relationship between pigments and culture, has argued that the loss of traditional pigments represents a loss not just of technical knowledge, but of meaning. In the ancient and medieval world, Bucklow contends, colours were not arbitrary. They carried significance that arose from the materials they were made of and the processes required to produce them. Ultramarine was precious, not only because it was beautiful, but because it was made from lapis lazuli, a stone that had travelled thousands of miles from the mountains of Afghanistan. Tyrian purple was valued not only for its hue, but because its production required the sacrifice of tens of thousands of living creatures. The colour and the story were inseparable. When you looked at a medieval painting and saw the Virgin's blue robe, you were seeing, Whether you knew it or not, a mountain in Central Asia, a caravan route across the Silk Road, a craftsman's months of careful grinding and washing. The color was a compressed narrative. Modern synthetic pigments carry no such narrative. Synthetic ultramarine blue is produced from a slurry of kaolin, soda ash, sulfur and charcoal heated in a furnace. The process is efficient, reproducible, and utterly without story. The resulting blue is chemically similar to natural ultramarine, but culturally empty. It references nothing. It connects to nothing. It is a color stripped of context, and something is lost in that stripping. Something that cannot be measured in wavelengths of light or chemical purity, but that nonetheless makes a difference to how a color feels. This may sound like sentimentality. It is not. Research in cognitive psychology and neuroaesthetics has demonstrated that human perception of color is not purely optical. It is influenced by context, meaning, and expectation. A viewer who knows that a blue pigment was painstakingly made from a rare and precious stone perceives that blue differently, measurably differently, in terms of aesthetic response, from a viewer who knows it was manufactured in a factory. The color is not just the wavelength, the color is the story, and the ancient world was rich in stories that we have impoverished ourselves by forgetting. The implications of this extend far beyond art. Every traditional pigment was, at its heart, a technology, a practical solution to a specific material problem, developed through sustained empirical investigation. The discovery of Maya blue was a breakthrough in materials science comparable to the development of modern polymer composites. The Egyptian mastery of high-temperature copper silicate chemistry anticipated principles of ceramic engineering that were not formalized in the West until the 20th century. The Phoenician development of Tyrian purple dye production was an achievement in biotechnology. The extraction and chemical transformation of a biological secretion into a stable, valuable product that has no rival in the ancient world. When these technologies were lost, the scientific knowledge embedded in them was lost too. Not the explicit knowledge of chemical formulas, which in most cases had never been formulated, but the implicit knowledge of how materials behave. Knowledge that, had it survived, might have accelerated the development of modern chemistry, modern materials science, and modern biotechnology by decades or centuries. We will never know. The counterfactual is as lost as the pigments themselves. What we do know is this: the history of lost pigments is a history of lost ways of knowing. It is a record of the systematic attrition of embodied, experiential, generational expertise, the kind of knowledge that lives in hands and eyes and the deep, slow accumulation of a lifetime's practice. It is a story about the things that fall through the net of written culture, the things that no archive can preserve, the things that exist only in the living chain of master and apprentice, and that vanish the moment that chain is broken. The Roman walls still glow, the Egyptian chests still gleam, the Maya temples still shine turquoise in the tropical sun. These colors are messages from civilizations that knew things we do not know, sent in a language we have forgotten how to read. They are not demanding our attention. They do not need to be decoded. They are simply, quietly here, radiant, patient, and beyond our reach. And the silence where the recipe should be is the loudest thing in the room. Think about what a single lost pigment represents in human terms. Behind every color on an ancient wall stands a chain of human beings stretching back centuries. A chain of masters and apprentices, each one learning from the last, each one adding some small refinement, some marginal improvement, some insight born of daily practice. That chain might stretch back 40 or 50 generations, 2,000 years of accumulated human experience, compressed into the motion of a hand-grinding pigment, the tilt of a kiln, the timing of a firing. When the chain breaks, when the last apprentice fails to learn, or the last master fails to teach, the entire accumulated inheritance of those 50 generations vanishes in a single human lifetime. Not gradually, instantly. The knowledge does not decay, it simply stops existing. The historian of technology, David Edgerton, has argued that our understanding of innovation is fundamentally distorted by a focus on invention at the expense of maintenance. We celebrate the moment of discovery, the first synthesis, the first application, the breakthrough. But the real achievement, Edgerton contends, is not the invention but the sustaining. The centuries-long tradition of practice that keeps a technology alive, refines it, and adapts it to changing conditions. Invention is dramatic, maintenance is invisible. And when maintenance fails, when the tradition of practice is disrupted, the invention dies, regardless of how brilliant it was. The Maya invented Maya blue. But it was the centuries of ritual practice that sustained it. When the ritual stopped, the pigment stopped with it. This is not an abstract point. It has concrete, measurable consequences. Consider the field of art conservation. When a conservator needs to restore a damaged area of an ancient painting, they face a choice. Use a modern pigment that approximates the original color, or attempt to source or recreate the historical pigment. In almost every case, the conservator uses a modern substitute, because the historical pigment is either unavailable or impossible to produce to the required standard. This means that restored ancient paintings are, in their restored areas, chemically and optically different from their original state. The difference may be invisible to the naked eye in normal lighting. Under ultraviolet light, infrared light, or spectroscopic analysis, the restoration is immediately apparent. A patchwork of ancient and modern, original and substitute, authentic and approximate. This matters because it means that our experience of ancient color is increasingly mediated by modern approximation. Every restored painting, every reconstructed mural, every reproduced pigment sample in a museum display case is a translation. And, like all translations, it loses something. The specific optical qualities of the original pigment, the particular way it reflects and absorbs light, the subtle interactions between pigment and binding medium and support. These are the qualities that made the original artwork what it was, and they are the qualities that modern substitutes cannot fully replicate. The conservator and pigment historian Nicholas Eastor has compiled what is perhaps the most comprehensive modern database of historical pigment materials, cataloguing over 10,000 individual entries with chemical, physical, and optical data. His work represents an extraordinary effort to preserve at least the analytical knowledge of historical pigments, even where the procedural knowledge of how to make them is lost. But Eastor himself has acknowledged the limitations of his approach. A database can tell you what a pigment is, he has said. It cannot tell you what it felt like to make it. And that feeling, that embodied understanding of the material, is where the real knowledge lies. The implications for our digital age are sobering. We live in a civilization that generates and stores more information than any in history. The global datasphere, the total volume of digital data created, captured, copied, and consumed each year, is measured in tens of zettabytes. A single zettabyte equals 1 trillion gigabytes. We have more data than we can possibly process, more information than we can possibly read, more recorded knowledge than any individual or institution can possibly absorb. We assume, with some justification, that this abundance of recorded knowledge makes us immune to the kind of catastrophic knowledge loss that befell the ancient world. After all, our knowledge is not held in the hands of a few craftsmen or inscribed on fragile scrolls. It is distributed across millions of servers, backed up on redundant systems, replicated in cloud storage centers around the world. But this confidence is misplaced. Digital storage is in many ways more fragile than the ancient methods it replaced. The average lifespan of a magnetic hard drive is 3 to 5 years. Solid-state storage fares somewhat better, but is still measured in years, not decades, and certainly not centuries. The formats in which digital information is stored become obsolete within decades. Try reading a floppy disk today, or opening a file saved in a word processing format from the 1990s. The institutions that maintain digital archives are subject to the same economic and political instabilities that brought down the ancient workshops. Servers require electricity. Electricity requires infrastructure. Infrastructure requires stability. None of these can be guaranteed over the timescales at which ancient pigments endure. The conservator and writer Mary Philadelphia Merrifield, working in the mid-19th century, spent years tracking down and translating medieval and Renaissance treatises on painting techniques, documents that had survived for centuries in library collections, but that were already becoming difficult to locate and increasingly fragile. Her compilation, Original Treatises on the Arts of Painting, published in 1849, preserved texts that might otherwise have been lost to the gradual attrition of time, neglect, and institutional indifference. Merrifield understood what many of her contemporaries did not, that written knowledge, however durable its medium, is only as permanent as the civilization that values it. Books are not immortal, she wrote. They are merely patient. Given enough neglect, even patience runs out. The pigments on ancient walls are more patient still. They require no electricity, no institutional support, no digital infrastructure. They ask nothing of us. They simply endure, in silence, outlasting the civilizations that created them, outlasting the languages in which their recipes were once described, outlasting the hands that applied them. If there is a message in their survival, it is this: the most durable form of human knowledge is not the kind we think is most important. The written word, which we venerate as the highest form of knowledge preservation, is fragile, vulnerable to fire, water, insects, decay, and the indifference of successive generations. The embodied knowledge of the craftsman, which we dismiss as mere skill, produced artifacts that have outlasted every library on earth. This is the deeper truth, the hierarchy of knowledge that our civilization has constructed, with theoretical, written, explicit knowledge at the top, and practical, embodied, tacit knowledge at the bottom, is inverted by the evidence of the pigments. The things we considered least worth preserving have proven most durable. The things we considered most worth preserving have proven most fragile. The great libraries are ash. The colours remain. Consider one final unsettling parallel. In the 20th century, the chemical company known as Binney and Smith, the makers of Crayola crayons, retired a series of crayon colours from their lineup over the decades. Colours like raw umber, maize, lemon yellow and blue-grey were deemed insufficiently popular and discontinued. The company, recognizing the sentimental attachment that adults felt toward the colours of their childhood, established a Crayola Hall of Fame for retired colours. The gesture was whimsical, corporate, and utterly trivial compared to the loss of Tyrian Purple or Egyptian Blue, but it contained an accidental truth. Even in our age of abundance, even in a market flooded with alternatives, the disappearance of a specific colour, even a cheap, mass-produced, industrially standardized colour, triggers a sense of loss out of proportion to its practical significance. Something about colour itself, about the way it connects to memory, identity, and the felt experience of being alive, makes its absence hurt. If we grieve for a retired crayon colour, what should we feel for the loss of colours that took centuries to develop? Colours that required the devoted labour of generations? Colours that were woven into the religious, cultural, and artistic fabric of entire civilizations. The appropriate response is not nostalgia. It is something closer to mourning. The philosopher Walter Benjamin, in his celebrated essay on the work of art in an age of mechanical reproduction, argued that reproduction strips an artwork of what he called its aura, the quality of unique presence that arises from a work's specific history of creation and existence. Benjamin was writing about paintings and photographs, but his insight applies with equal force to pigments. The aura of an ancient pigment, the unrepeatable quality that arises from its specific raw materials, its specific process of manufacture, and its specific history of survival, is precisely what modern reproduction cannot capture. Synthetic ultramarine has no aura. Factory-produced cinnabar has no aura. They are copies without originals, echoes without sources, colours without stories. And this loss of aura, this loss of the irreducible specificity that makes each ancient pigment unique, may be the deepest loss of all. It is not a loss that can be measured in chemical terms or expressed in spectroscopic data. It is a loss of meaning, of the dense web of associations, experiences, and knowledge that connected a colour to the world that made it. When that web is severed, the colour may persist, but it persists as a ghost, a visual echo of something that was once incomparably richer, and the rate of loss is accelerating. In the middle of the 20th century, there were still communities around the world where traditional pigment making survived as a living practice, where the chain of master and apprentice remained unbroken, where embodied knowledge was still being transmitted, where the ancient traditions still had a heartbeat. Today, In every one of those communities, the pulse is weaker, the masters are older, the apprentices are fewer. The economic pressures that drive young people toward more profitable livelihoods grow stronger with every passing year. The anthropologist Tim Ingold has argued that the loss of craft traditions represents a kind of amputation, the severance of a limb of human capability that, once removed, cannot be regenerated. Skills are not possessions that an individual either has or does not have, Ingold writes. They are properties of the whole system of relations that includes the person, the tools, the materials, and the environment. When any part of that system is removed, the skill ceases to exist. This systemic view of craft knowledge explains why it is so difficult to revive a lost tradition. You cannot revive a relationship by reassembling the individuals. The relationship itself, the dynamic, living, responsive interaction between maker, material, and method, must be rebuilt from scratch. And rebuilding takes generations, not grants. The most sobering realization is perhaps the simplest one. We are not at the end of this story. We are in the middle. The loss of ancient pigment knowledge is not a completed event, but an ongoing process. Right now, today, at this moment, the last practitioners of traditional pigment and dye traditions around the world are carrying knowledge that will die with them unless something changes. The cochineal dyers of Oaxaca, the indigo craftsmen of Japan, the natural pigment producers of India and Africa, they hold fragments of a heritage that stretches back millennia, and those fragments are slipping through our fingers, even as we speak. We could preserve them. The tools exist. Video documentation, apprenticeship programs, research partnerships between scientists and traditional craftspeople. But preservation requires resources, and resources follow priorities, and our civilization's priorities lie elsewhere. We fund particle physics and artificial intelligence and space exploration, pursuits that are magnificent and worthy. But we do not, with anything like comparable urgency, fund the preservation of the embodied knowledge that connects us to our material past. And so the knowledge continues to drain away, silently, one practitioner at a time, while the colours on ancient walls continue their patient vigil, enduring, luminous, and unreachable. What does it mean for a civilization to forget how to make a colour? The question sounds trivial. It is not. Colour is not ornament. Colour is information about materials, about processes, about the relationship between human beings and the physical world they inhabit. A pigment is a compressed encyclopedia of geology, of chemistry, of biology, of craft. When a pigment is lost, an encyclopedia is closed. We began this story with a shade of red on a wall in Pompeii. A red that has survived nearly 2,000 years of exposure and that no modern laboratory can exactly replicate. We travelled from there through the oldest synthetic pigment in human history, through the dye that dressed emperors, through a material that exhibits quantum mechanical effects that were not even conceptualized until the 20th century, through a nanocomposite that should not exist, through a yellow that was produced by the metabolism of living animals. In each case, we encountered the same fundamental truth, that the ancient world possessed a kind of knowledge that our civilization has lost the capacity to hold. That knowledge was not inferior to ours, it was different. It operated through different mechanisms, through embodied practice rather than theoretical understanding, through sensory perception rather than instrumental measurement, through generational transmission rather than written documentation. It was fragile in ways that theoretical knowledge is not, because it depended on the continuity of living human chains of practice that could be broken by a single generation of disruption. But it was also powerful in ways that theoretical knowledge is not, because it could achieve outcomes that no theory predicted and no formula can reproduce. The implications for how we think about knowledge itself are profound. We live in an age that treats written, explicit, digitally stored information as the only real form of knowledge, as the sum total of what humanity knows. Everything else, the feel of clay under a potter's hands, the smell of a properly fermenting dye vat, the instinct that tells a glassblower to stop heating at the precise right moment, is dismissed as subjective, unreliable, anecdotal. Not knowledge, just experience. The pigments disagree. The pigments say that experience is knowledge, that the hands know things the books do not, that a tradition of practice, maintained over centuries by unnamed craftspeople whose names no history records, can produce outcomes that surpass the capabilities of the most advanced laboratories on Earth. This is not a romantic claim. It is a factual one, supported by spectroscopic evidence and confirmed by the repeated failure of modern science to fully replicate ancient materials. And so the question for our civilization is not whether we value the knowledge of the past. We clearly do, as the billions spent on museums and conservation attest. The question is whether we value the kind of knowledge that the past held, whether we are willing to recognize that embodied, tacit, experiential knowledge is real knowledge, worthy of the same respect, the same resources, and the same urgency of preservation that we extend to written texts and digital databases. Whether we understand that when the last traditional pigment maker dies, the loss is not merely sentimental but epistemological, a permanent reduction in the total stock of human understanding. The answer so far is no. We have not recognized it, we have not funded it, we have not prioritized it, and the knowledge continues to drain away, drop by drop, color by color, hand by hand, into the silence that comes after the last craftsman. Are we making the same mistakes that cost the ancient world its pigments? The parallel is uncomfortable. We, too, concentrate knowledge in the hands of specialists. We, too, rely on systems, digital systems, institutional systems, economic systems, that are more fragile than they appear. We, too, assume that knowledge once acquired stays acquired. The people of Roman Pompeii assumed the same thing. The Maya of Chichen Itza assumed the same thing. The craftsmen of Han Dynasty China assumed the same thing. They were all wrong. And the most unsettling part, we may be doing the same thing right now. Not with pigments, with everything. Every skill that exists only in human hands, every expertise that resides only in living practitioners, every tradition that depends on the unbroken chain of master to apprentice is as vulnerable today as Egyptian blue was in the 5th century. The chain can break at any time, and when it does, the knowledge it carried is gone. As gone as the recipe for Tyrian Purple, as gone as the method for Maya blue, as gone as the process that produced the luminous walls of Pompeii. What followed the ancient destruction of colour knowledge was not anger. It was silence. The worst kind of silence. The silence of things that can never be made again. That silence is growing. There is a wall in the ruins of Pompeii where the red paint is still so vivid that visitors sometimes reach out to touch it, as though unable to believe that something so bright, so alive, could be so old. The guards stop them. The red does not need protection from fingers. It has survived earthquakes, volcanic eruptions, 2 millennia of weather, and the curiosity of millions. It will survive a touch. But the guards stop them anyway, because something about the colour demands reverence, demands the distance that we keep between ourselves and things we do not fully understand. That red is a message. It says someone knew how to do this. Someone, in a workshop in a Roman city, working with tools that would seem laughably crude by modern standards, produced a colour so stable, so luminous, so perfectly suited to its surface, that 20 centuries of time could not diminish it. That person's name is not recorded. No text describes their method. No student preserved their technique. They are as anonymous as the colour is vivid, and the gap between their anonymity and their achievement is the gap at the centre of this entire story. What humanity lost when ancient pigment traditions died was not merely a set of recipes. It was a way of knowing, a way of relating to the material world that was intimate, patient, and profound, a relationship built over centuries of daily contact between human hands and the substances of the earth. Rock and mineral, plant and insect, heat and time. The ancient pigment makers understood these things not as abstractions but as presences, as partners in a process that required respect, attention, and the slow accumulation of wisdom that no shortcut can replace. We cannot get it back. That is the honest answer to the question in the title. We cannot reproduce these pigments. Not fully, not faithfully, not in the way that the ancient craftsmen made them. We can approximate them, we can analyze them, we can come tantalizingly, heartbreakingly close. But the last few percent of difference, the difference between a modern recreation and the ancient original, is the distance between knowledge and understanding, between information and wisdom, between knowing what something is and knowing how to make it sing. The numbers tell part of the story. Of the major pigment traditions developed by the ancient civilizations of Egypt, China, Mesoamerica, Rome, India, Phoenicia, and the medieval Islamic world, the majority have been either lost entirely or degraded, to the point where full reproduction is impossible. Fewer than 1 in 3 ancient pigment-making processes can be replicated to a standard that matches the surviving originals. The rest are gone, not destroyed by any single catastrophe, but eroded by the slow, quiet, relentless action of forgetting, neglect, economic change, social disruption, the simple failure to pass knowledge from one generation to the next. These are the forces that killed the ancient colours. Not fire, not war, just silence. And that is perhaps the most frightening thing of all. We expect knowledge destruction to be dramatic. A burning library, a sacked city, a deliberate act of violence against the written record. Those events make for powerful stories, and they are real. But the greatest losses in the history of human knowledge were not dramatic. They were quiet. They were the thousands of moments, unrecorded and unnoticed, when a master craftsman died without an apprentice, when a workshop closed for lack of customers, when a tradition, sustained for centuries by the patient labor of anonymous hands, simply stopped, not because anyone decided to end it, but because no one decided to continue it. The wall in Pompeii does not mourn, the blue on the Egyptian chest does not weep, the turquoise at Chichen Itza does not cry out for what has been lost. These colors endure in silence, the same silence that swallowed the knowledge of how to make them. They are the most beautiful tombstones in the world, monuments to expertise that was once as alive as a beating heart and is now as still as the stone on which it rests. If every lost pigment recipe could be recovered, every firing temperature, every grinding technique, every mordanting sequence, every fermentation timing, the collected knowledge would fill not a single book but a library of hands, a library of senses, a library of 10,000 generations of human beings who learned, through daily practice, how to coax beauty from the raw materials of the earth. That library was never built. It existed only in the people who carried it, and those people, one by one over centuries and millennia, took their volumes to the grave. The colors that survive on ancient walls are the last pages of that unwritten library. They are all we have. They glow with a light that no modern pigment matches, a light that comes not just from chemistry but from the accumulated human effort that produced them. Effort measured in lifetimes, in generations, in the slow, irreplaceable patience of hands that knew what they were doing. When you stand before an ancient painted wall and feel something you cannot name, something beyond aesthetic appreciation, something that feels almost like grief, you are feeling the weight of that effort. You are sensing the presence of knowledge that once existed and that exists no longer. You are standing at the edge of an absence so vast that it cannot be measured, only felt. Somewhere, tonight, the last practitioner of an ancient color tradition is at work, grinding pigment, tending a dye vat, firing a kiln by the light of a method that was old before any living nation was born. That person holds, in their hands, knowledge that no database contains and no textbook describes. Knowledge that was ancient when it was first taught to them, and that will be ancient when they can no longer teach it. The question is not whether that knowledge is valuable. The evidence is on the walls. The question is whether anyone is learning it. The red in Pompeii has not faded, but the hands that made it are dust, and no amount of science, no amount of longing, no amount of regret can bring them back. The color endures, the knowledge does not. And that, quiet, irreversible, permanent, is the loss.